So this video is to give you a little bit of history about the different models of the atom that we have considered, and to bring you up to the current model here in Module 7, we finally get to the quantum model of the atom. So we're going to go from Dalton's model through J.J. Thomas's model, through Ernest Rutherford's model, through Niels Bohr's model, and then finally to Schrodinger's model. Let's have a look at that. So just a quick review. Dalton said this, that all matter is composed of individual particles called atoms, okay? And that by definition, an atom is indivisible. You can't, he uses the Greek word atom, and it comes from the Greek word atomos, which means you can't cut the thing into parts. And his other conclusion was that all elements of this, all particles of the same element, they have exactly the same particles. So if you have one atom of carbon, it's going to react in a chemical reaction just the same as any other atom of carbon. William Crookes challenged the idea that they were indivisible. He used what we call a cathode ray tube, and he was able to bombard atoms with energy and knock off particles. And he called those cathode rays, and we now know those cathode rays to actually be electrons. And so what he figured out was that it isn't true that the atom is indivisible or unbreakable. You can actually knock some things off of it, and electrons were examples of what you could knock off of it. Here's a picture of a cathode ray tube. You have charged particles that are moving. He has a target right here, and you can see the shadow of the target there. And from this test, he was able to show that they're particles and not just light. Well, that led to the plum pudding model of the atom. If you can knock things off the atom and they are negatively charged, and we now know that that is what an electron is, then we're going to devise an atom that has just such a thing in it. And so here we have an atom which is positively charged as a whole, not individual positive charges in there, but it has negative little raisins on it, and it's called the plum pudding model. Ernest Rutherford wanted to test the plum pudding model, and so he believed that if the plum pudding model was true, then he ought to be able to bombard an atom. He's going to bombard a gold atom with positively charged particles. These are actually what we call alpha particles, and they are nothing more than 2 protons and 2 neutrons together, and that is the equivalent of a helium nucleus, by the way. And then if he bombarded these gold atoms by it, that if the plum pudding model was true, he believed that the alpha particles wouldn't be deflected in any way. They would actually go straight through the gold atoms, and he would be able to detect them on the other side. So he devised a little experiment this way. He had an alpha particle emitter, and he had it closed in, and he basically built a little gun that shot off alpha particles. And then he had some thin gold foil as the target, and he put a detector behind the gold foil, and he was testing to see whether these alpha particles just basically went straight through. And for the most part, that's exactly what happened. The 99.99% of all the alpha particles that he expected, that he was shooting through, he was able to basically detect those on the other side. But just out of curiosity, he moved his detector away from behind it just to see if by any chance he would ever get any hits anyplace else on his detector. And so, for example, when he moves his detector down a bit, shockingly, sometimes, not very often, he would actually get a hit on his detector of alpha particles colliding with his detector in a location that he wasn't expecting it. And even more shockingly, if he even moved the detector in front of the gold foil, he said that some of those alpha particles would be deflected at really hard angles, almost straight back at the source. And he was so shocked by that, by the way, that he compared this to, he says, let's say that I have a cannon, and I put a piece of toilet paper out in front of the cannon, and I shoot that cannonball at the toilet paper. He said, it doesn't surprise anybody that that ball is just going to go right through the toilet paper undeflected. But he said, sometimes it's like I shoot a cannonball at that piece of toilet paper, and that cannonball bounces right back at me. And anyway, it just blew him away. But what he concluded, of course, was that sometimes, not very often, but sometimes he would hit the nucleus of one of these gold atoms, and that nucleus was inconceivably small but inconceivably dense, and it would either deflect a helium particle off uh, or even send it almost straight back at him. That was Rutherford's conclusions.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom is empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, what we're doing here, is taking a beam of particles, firing it at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom by comparison is very big, so it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
Okay, so let's summarize what we have learned about Ernest Rutherford and his model of the atom. What Rutherford concluded was that the atom exists basically like planets orbiting around the sun. And the planets are the equivalent of the electrons, and the sun is the equivalent of the nucleus of the atom. And interestingly enough, just like between the Earth and the Sun, the atom is mostly empty space in between the Earth orbiting around the Sun, and the electrons are the outside of the atom, and it's mostly empty space in between the electrons and the atom. The other thing is that the nucleus is almost inconceivably dense compared to the atom itself, and it's also inconceivably small in comparison to the size of the atom. So those are the main things to take from Ernest Rutherford's model of the atom. Our next contributor to the structure and the makeup of the atom would be Niels Bohr. And Niels Bohr is going to be working with the hydrogen atom. And in particular, he's going to be looking at atomic spectrum of hydrogen atoms that are in a vacuum tube. So there's very little atmosphere, but there's mostly just hydrogen in the vacuum tube. And they're going to run a current through it. And you're going to see light that's emitted off of those hydrogen atoms in there. And that light looks like this. You get this distinctive red kind of purplish glow that's a part of that. Well, what people were doing, not just Niels Bohr, but other people were doing, is that they were looking at the spectrum. They would run this through a prism, and they would see the different bands of light that came off of that light emission right there. So in comparison to, let's say that rather than looking at the hydrogen, let's say that you just looked at the light from the sun. If you run that light through a spectrum, you get the full spectrum. You get the high energy end over here in the blue and the ultraviolets, and you get the lower energy in the reds over there. Well, whenever they looked at the spectrum of the hydrogen source, you see only distinct bands. You don't see all of these blues and greens and reds. You just see individual bands of light that came up every time anybody ever looked at the spectrum of hydrogen. And if we would flip this around, we could also talk about the fact that hydrogen would absorb light at those same exact spots. So let's say now you're looking at the full range of sunlight, and if you were to be looking at the hydrogen as sunlight passes through hydrogen, it would actually be absorbing light at those same frequencies right there. So the question is, where do these bands of light come from? Why do they exist? Why do they exist right here? Why do we get one red, one green, and a blue, and then one violet? Why do we get that? And so Niels Bohr proposed this as an answer to it. He says, let's say that you have a hydrogen atom, and the hydrogen nucleus, of course, is in the center here, and it's inconceivably small, so you don't even see the nucleus. But this first circle here is an energy level where the hydrogen electron exists. So there's a nucleus in there that's positively charged, the proton, and there's one electron that hangs out at this certain energy level. Well, if you hit that hydrogen atom with enough energy, whether it's heat or light or whatever, you could excite that electron from the n equals 1 or n equals 1 to the n equals 2 level. Or if you even hit it with more energy, you could excite it from the n equals 1 to the n equals 3 or the n equals 4 that I don't show, or the n equals 5, or there's virtually an infinite number of possible orbits there. And that those light bands that we saw, those bands actually occur when that electron de-excites. When it falls back to a lower orbital, or even all the way back to its ground state, it emits a photon of energy. And that energy corresponds to the energy of the orbit that it fell from. Let's look at another spectrograph here. So we call a spectrometer just something that allows you to look at the bands of light. And here's another spectrometer of the hydrogen atom, and you can see we have the distinct red band, we've got the blue There should be a green band in there. I guess that's the green, and then should be a blue and then a violet. And they're called spectrometers because they have virtually ghost-like images. And so that's where we get the word spectrometer. Well, we'll look at the numbers on the hydrogen spectrum. So here is back to the hydrogen emitter. That's the light that you would see with the naked eye. If you run it through a spectrum, what you find is, now I flipped this down, always before I had the low energy down here, but we're going to flip this on the other side, that you have a red band, a green band, a blue band, and a violet band. And that red band always appears at 656.2 nanometers. The green is 486.1 nanometers, the blue 434, and then the violet 410. That those are where you always find these bands. So just to go back, I mentioned that it's found at 656.2 nanometers, but I didn't correctly point out that they're not just found there. That's the wavelength of that light. And the wavelength of this green light is 486.1. By the fact, so anytime you see green light, it's going to have a wavelength something like that. Anytime you see red light, it's going to have a wavelength something like that. And so what we're looking at here are energies, we're looking at wavelengths of energy, and we're able to separate them with a spectrometer and with our eyes based on color. All right, so now we're going to try to tie the fact that we have this hydrogen spectrum of light to the actual structure of the atom. That's what we're actually doing here. So Bohr concluded this, that you have negatively charged electrons. They have obviously exceptionally small mass, but they travel in quantized orbits around the nucleus. They can't just have any orbit at all, but they have defined orbits that are going to exist. So here's an n equals 1 orbit, and you can have an n equals 1, but you're never going to have an n equals 1.5 or 1 3/4, but you could have an n equals 2. So it's a quantized orbit. N is the energy level of that orbit, and that electrons travel in these orbits, and that what you could do is you could excite them to a higher energy level. So this electron here, it could be excited up into an n equals 2 level, or this n equals 2 electron could go up to an n equals 3 or 4 or 5. And the energy that's possessed by those electrons in the hydrogen atom and the radius of its orbit, they are distinctly quantized. And he calculated the values of those quantized energy levels using an equation containing an integer. So n equals 1, 2, 3, 4. And we're going to read that energy level, by the way, right off the periodic chart of the elements. And I'll show you what I mean by that in a second. Electrons, they can move between orbits. If you hit them with some energy, they can do what we call a quantum leap. They can jump from a lower energy level up to a higher energy level. And here's a picture of what that looks like. Let's say that you have an electron in this ground state, that's the n equals 1 level, and you hit it with some energy. It could be energy in the form of light, it could be energy in the form of heat, whatever it is, and you excite that electron. So it's no longer in this n equals 1, but now it's jumped up to the n equals 2 level. Well, it can only stay up there for a little while because it took energy to drive it up there. Unless you just keep that energy pumping, what's going to happen is that electron is going to drop back down to the ground state. And when it does, it emits a photon of light that is exactly equal to this energy level, n equals 2, as it falls to the ground state. Well, this summarizes Bohr's contribution. What he ends up doing is successfully explaining the lines in the spectrum of a hydrogen atom, and he predicted that new lines would exist, and that was proven to be correct. And he introduced the idea that the electrons have to exist in quantized orbits or at quantized energy levels. One of the problems with doing much with Bohr's model is that it really only works for the hydrogen atom, or it could work for any atom that just has one electron in it. The other problem is this, that given the current laws of physics, this charged body moving in a circle radiating energy, it should end up crashing down into the nucleus, and we know that it doesn't. And so nobody could explain why that electron, if it was moving in a circle radiating energy in the form of the light that we saw in the spectrum, why it wasn't crashing down to the nucleus. This is what the current physics would have projected, that if you have an electron, it's got a vector velocity, that if it is moving, sure enough, it would be emitting light, but eventually it's going to end up in the nucleus. And we know that electrons don't end up in the nucleus. Something is keeping them out of the nucleus, and that is the fact that electrons can only exist in quantized orbits. And we couldn't explain why that was without quantum mechanics. And that's what we look at next. So the quantum mechanical model is a mathematical model. It's all going to be talking about the probable location of an electron in an atom, rather than Niels Bohr. He talked about the radius of an electron from the nucleus. We're going to have to let go of the idea of the radius, and we're going to just talk about the probable location. And Schrödinger is our scientist who figured out that the atom really doesn't have electrons moving in orbits around a nucleus, but it has an atom has electrons that move in orbitals. They're actually quantized energy levels. And this will be a picture of the quantum model. So in Bohr's model, you would have a very defined radius. But in the quantum model, really look at this. You have all of these dots that represent the probable location of an electron at a certain energy level. And sometimes you end up with a dense cloud, and that would be the most probable location. And that's what the quantum model is going to work with. So just really quick summary of some of the things we've said. The quantum model deals with orbitals that exist in clouds rather than orbits. So we're not going to talk about an orbit with a certain radius. We're going to talk about orbitals, and those are clouds with specific energy. And they have shapes. The shapes of these clouds can be described by quantum numbers. N equals 1, N equals 2, N equals 3, that's the N level. It can be described by this L value, which talks about different shapes within that same energy level. It can be described as an M sub L level, which talks about which individual shape it holds, and then the spin. And in our class, we're not going to really deal with the quantum numbers. We're just going to talk about these orbitals as being SPD orbitals, those shapes. All right, so let's look really quickly at this is your periodic chart of the elements. It looks a little bit different than what you've looked at before. We don't actually show you any of the elements that are in there, but we're trying to highlight the energy levels that the electrons will hold that are in their highest energy levels. So for example, I have 1, 2, 3, 4, 5, 6, 7. These would be energy levels, like a 1s. That's energy level 1. A 2s is an energy level 2. You also, at that energy level 2, you have not only s, but you have p electrons. You can go to an energy level 3, where you have 3 s electrons, 3 p electrons, and you also have d electrons that are in that third energy level. And I'll stop at that point. But what we're going to do in this class is we're going to have you predict what the highest occupied energy level of an electron will be in a given atom. So, for example, this is how we're going to go about doing that. Let's look first off at the sodium atom. If you would look at sodium on the periodic chart of the elements, he's going to be located right here in this third energy level block. All right, and he is located in what we call the S block. He's not located over here in the P block, and he's not located down there in the D. On the periodic chart of the elements, he sits right there. And so what we're saying is that sodium, we know that he has 11 electrons total because, he has the same number of electrons as protons, and his atomic number is 11. But what we're saying is that the electrons with the highest energy, they are going to exist in this 3s subshell. All right, so now I'm going to have you do it. I want you to look for calcium and tell me what the highest energy level of its valence electrons is. So find calcium on the periodic chart of the elements. And calcium is going to be located right here in this 4s block. And so what you're going to tell me is that calcium, its valence electrons are located at an n equals 4 level, energy level, n equals 4. That just comes right off the periodic chart. And they are s orbitals. How about aluminum? Find aluminum on this chart. Aluminum is located right here in the 3p orbitals. And so you're going to say that its electrons are the highest energy electrons in the orbit around an aluminum atom are going to be 3p electrons. And you know that there are, 13 electrons total, so they're not all there, but the ones that are the highest energy level, they're there. You actually have electrons that exist in the 3s orbitals, the 2p orbitals, the 2s orbitals, and the 1s orbital. But if you add all of those up, eventually you get to 13 electrons, and that last electron is right here in this p orbital, in the 3p. How about fluorine? Where's fluorine at? If we look on the periodic chart of the elements, fluorine is located right up here in this top right-hand corner. And so what we know is that fluorine, he has an atomic mass of 9, so it's got 9 total of electrons, but it has 5 of those electrons in the 2p shell, 2 here in the 2s, and then 2 in the 1s, and that gives you the total of your 9 electrons. Let's look at bromine. Where's bromine? Well, bromine is over here down under fluorine. So we got fluorine, chlorine, bromine right down here. So he is in the energy level equals 4. Now, bromine has a bunch of electrons, keep in mind. It's got 35 of them. We can tell because its atomic number is 35. But what we say is that the highest energy level that his electrons occupy, and just in their ground state, is right there at that 4p 5 level. So some of those electrons in bromine are going to be in this 4p area. Others are going to be down in the 4s. Others are going to be in the 3d, the 3p, the 3s, the 2p, the 2s, and the 1s. So you add all of those electrons up, and of course it'll come to 35. But the point here is you need to know that the highest energy level that the electrons of a bromine atom are found in, and if they're in their ground state, it's at this 4p level. So let's take another step into this. We're actually going to define basically what we're going to call here an address, which the address just tells us the energy level of the highest valence electron. So sodium is going to be right here. Sodium is atomic number 11, and we're going to say that his address, or the highest energy level electron he has, is an energy level n equals 3. It's an s orbital because it's in this s block here, and it's 3s1 because it's in the 1 column. Okay, now let's look at calcium. Where is calcium located here, and what might we call its address be? Well, Calcium is in the 4s block. It's atomic number 20. And so what we're saying is that if we were to give an address for the highest electrons, highest energy level electrons, we would call that address 4s2 because it's in this column 2 and it's all the way up to 4s. All right? How about aluminum? What would aluminum's so-called address be? Well, aluminum is atomic number 13, and so we're going to call it a 3p1 because it's in the first of these 6 blocks of p electrons that you could have. So it's going to be a 3p1. It's got 1 electron in that p block. And then, of course, you know that it's got 2 electrons in the 3s block. It's got 6 electrons here in the 2p. It's got 2 more in the 2s, and then it's got 2 more in the 1s. But that's the electron configuration for aluminum. Now let's look at fluorine again. Fluorine, we talked about him being over here, atomic number 9. All right, so we're going to say that his address, so to speak, is going to be 2 because it's in this energy level 2, and P because it's in the P block, which is this green, and we're going to say 2P1, 2, 3, 4, 5. 2P5 would be its highest energy level in the ground state for its electrons. Now you could go through and you could answer all of these with these other elements as well. You go through bromine and lithium and titanium and silver and gold and platinum and mercury. All you have to do is find them on the chart, and then you can predict the highest energy level of their valence electrons just based on where they fall in the chart. So if we would, let's just grab one of these, gold here, right? Gold is number 79. So gold is number 79, and he exists in this D block. That's this big block here. And what we would say that his address would be a 5D 1, 2, 3, 4, 5, 6, 7, 8, 9, 5D9 electron. That would be the highest energy level that an electron would have in a ground state gold atom. All right, so it turns out that these different orbitals, the s, the p, the d, and the f, and keep in mind the s, p, d, and f, we read those right off the periodic chart. S orbitals are nothing more than a sphere. And an s orbital is going to be assigned a quantum number of a 0. And we don't actually deal with this number in first year chemistry, so I won't say much more about it. But all s orbitals are going to have an L value of 0. All p orbitals, there are actually 3 different possible shapes. They're kind of these dumbbell shapes that exist at right angles to each other. They are going to have those shapes. The d orbitals, a little more complicated than that, and there are 5 of those, and there are 7 f orbitals that exist. And so you need to be able to, if I ask you what is the shape of an s orbital and how many electrons can be in an s orbital, you're going to tell me the shape is a sphere, and there can only be 2 electrons, by the way, in any one of these orbitals. In the p, we have 3 different possible orbitals in the p, and you can still only have 2 electrons in them, but this is 1 orbital there. That's not 2, that's 1 orbital in that shape, and you can have 2 electrons in this orbital, 2 electrons in that orbital, and 2 electrons in that orbital. Same thing with the D. The D has a more complicated shape yet, and there are 5 of the different shapes that can exist, but each of those shapes can only have 2 electrons in each orbital. So the D orbital can have 2 in this shape, 2 in that shape, 2 in that shape, 2 and 2, and so on. So as you increase in size of atom and energy level, you can hold more electrons in those energy levels. All right, so let's look at some examples if we're going to just outline the position and the energy level of electrons in different atoms. So we know that hydrogen has got 1 proton and 1 electron, remember, because it's number 1 in the periodic chart. And so it exists at our energy level of n equals 1. That's where this 1 is. And because there's only 1 electron possible in a hydrogen atom, that electron exists in the s orbital, which is in the shape of that sphere, and we call it a 1s, 1 electron. Helium, it's going to have 2 electrons, and so it is still in the energy level n equals 1 level. It runs right across the top of the periodic chart, but it's got 2 electrons in it, and so we're going to say that the highest energy level for its valence electrons are 1s2 electrons in their ground state. Let's look at carbon here. Now carbon, you see him, carbon is atomic number 6, and so that means it's got 6 protons and 6 electrons. And here we're accounting for all the electrons in the carbon atom. It starts off, you fill the lowest first. So we start off with, we have 2 electrons in the 1s energy level. We have 2 more electrons in the 2s energy level. And then we have 2 remaining electrons, because we only have 6 total, so 2, 4, 6, that exist at the p level. And that's how we give a notation for the electrons in these atoms. Once again, the shapes. So the hydrogen, it's got 2 electrons that are in the 1s orbital, and they are in a shape like a sphere. Carbon, though, has got 2 electrons that are in the 1s, and it's got 2 more that are in the 2s, and because it has 6 electrons total, it has 2 electrons in these p orbitals. And we're going to put one of those electrons in one of the p orbitals and one of the electrons in another p orbital. That's how we are filling our subshells based on energy level and orbitals. All right, so now the practical part of this. If we want to write the electron configuration for an atom like neon, what we first have to do is go to our periodic chart of the elements and figure out how many electrons we have to work with total. And so if I go to neon, I find that he's element number 10, so that means I have 10 electrons that I can work with. And in order to do the write the electron configuration, I'm going to fill those electrons in the lowest energy levels possible and then build up. And I'm not going to get very high with neon. But I know that neon is found, by the way, if I were to give its address, that's going to be a 2p6. So we're going to head all the way up to here. I know that my last electron is going to be in this spot here. But I'm going to find those 10 by, I'm going to put 2 here, 1, 1, 1, then 1, 1, 1. So I get 2, 2, and then 6. And that's going to give me 10 electrons. And so I would say that I have 1s2, 2s2, 2p6. That would give me my electron configuration for neon. Now we're going to do the same thing with sodium. If I look at sodium, sodium is just one more. He's got an atomic number 11, so he has 11 electrons. So I'm going to put 2 of those electrons here, so I have a 1s2. I'm going to put 2 more in there. I'll have 2s2, and then I'm going to put 6 of those electrons here. I'm going to have 2p6, and then I'm going to have 1 electron right there in my 3s1. If I do aluminum, now aluminum is atomic number 11. And so I know that I have, 13, not 11. Aluminum is 13. I have 13 electrons to work with. So I'm going to start by putting them here. I'm going to say, okay, I got 2 here, 2 here, 6 there. That gives me my 6, 10, and then 11, and then 12, 3s. And then finally I get to one of my p's. That's going to be my 3p. So my final electron is going to be in a 3p1 orbital. Argon. Let's look at argon. Argon is one of our noble gases. It's got 18 electrons total, and it is in the 3p block. So argon is going to be, I start off to fill my electrons. I have put 2 down here, 1s2, 2s2, or 1s2, 2s2, 2p6, fill all of those, 3s2. and argon is my last one that I can put in this P block, and so it's going to be 3p6. It's going to be existing right there. Bromine, let's do that one. Bromine has 35 electrons, and it's going to exist in my n equals 4 block. So I'm going to be all the way up here to the 4p whenever I do my bromine. And I'm going to fill all those electrons in all of these subshells, excuse me. So I got 35 that I can put in here. So I'm going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, that's where I'm actually, now I lost track. I got to look at that one more time. Yeah, I just got wild. So I can't go in any farther than my 3p5. That's as high as I can go with my bromine because he's only got 35 electrons. All right, let's try this bromine. So bromine, if I look on it, it is at the energy level of 4, and it exists in my P block. It's got 35 electrons total, and so if I'm going to fill those from the bottom up, I'm going to go all the way up to my 4p5 spot. So I could put one electron right there, and then I could fill all of these others. So I'm going to say I'm going to have a 4p5, that includes all of those there, and then 3d10, 4s2, 3p6, 3s2, 2p3, 2s2, 1s2. That would be bromine. Yeah, and you can do it for any other atom in our chart. All right, just a quick review of the shapes that we're talking about. So s orbitals look like a sphere. P orbitals have a dumbbell shape, and there are three possible p orbitals, and you can have 2 electrons in each of these p orbitals. So keep in mind that that's not 2 orbitals, but you can have 2 electrons in that orbital. Of course, when we fill them one at a time before we start adding 2 electrons in any given orbital. So our s orbitals, I can have 2 electrons here in an s orbital, and keep in mind we have 1s, 2s, 3s, 4s, 5s, so there's lots of different s orbitals. They're just different sizes, but each s orbital can only have 2 electrons. I have 3 different shapes of p orbitals, and each of them can have 2 electrons in them, so I can have a potential of 6 electrons in my p block. And my d, I have 5 possible shapes that exist, and I can have 2 electrons in each of those. So that means in my D block, I can have up to 10 electrons, and then we can go to our F electrons and talk about the 14. So that's what you need to know about the shapes of the orbitals and writing out the electron configuration of electrons in those orbitals. All right, so in this video, we've covered a lot of ground. We've covered history. We've covered the light spectrum, and we've also talked about the shape of the orbitals and the electron configurations. The only one more thing we're going to want to do is I'll produce another video where we work with light and the wavelengths and the frequencies and the energy. That we'll do. I just set that aside with the mathematics of light and the spectrum. We talked about the theory, we talked about seeing the different spectrum patterns in the hydrogen spectrum in particular, but I'll do one more video that just where we deal with the math of how to work with that. Anyway, this is still Module 7.